Hey folks, welcome back to another video. Today we're looking at question 1277, count square submatrices with all ones. The way we'll be approaching this problem is by using dynamic programming. So let's look at an example. Let's consider the matrix that I've highlighted as the input. The answer that we should get is 5. Right, so it's we have 4 squares of size 1 and then a 1 square of size 2, so the side is equal to 2. So the way we'll be handling this is that we will be iterating through every single row and every single column, and so this is what the DP matrix will look like. If the value of the matrix is 1, you look at the top cell, the cell to the left, and the cell that's diagonally on top to the given cell. So right now, since this is this is at the corner, you don't do anything. We just have it as 1, and we just add the number of squares that we've seen so far to be 1. We do the same for this square right here. We come here, the same case, and then as soon as we come here to the last cell right here, we see that everything surrounding it, which is to the left, to the top, and diagonally north, we see that all of them are 1. So and the current cell is also 1. So this could potentially make a square, right? So to be able to compute that, what you'll be doing is that to get a minimum of all of the cells surrounding it to the left side. So left, top, and diagonally north, like all of these cells, you get the minimum of all of them and you add 1 to that. So what does that mean? If all of them are 1, that means it could potentially form a square, and you just take the minimum of that and add 1. So that would be 2 squares. So at this particular point, you can form a square of size 2. But if it was 0 right here, you wouldn't really do anything, because the given cell is it's not 1, so you don't do anything. However, if this was 0 and this was 1, and you are at the last cell, like the bottom right cell, and you check, hey, can I form a square with this, like a square of size 2? And you look at all of the surrounding cells to the left, but one of them is 0. So that's the reason why you take minimum. You take minimum and then you add 1 to that. So the minimum is 0 and you add 1. So that's the reason why this formula works. So I hope that made sense. Let's jump right in with the solution. Let's get the number of rows and columns first. So let's do that. And length. This would be the number of rows. Number of columns would be matrix of 0.length. And then you'd have result, which is equal to 0. You would have a for loop. You'll do something within the for loop, and in the end, you would want to return the result. Return result. Awesome. Instead of forming a new 2D array where we would keep a track of the cells that we've seen so far, we can override the existing array that we have, because once we iterate over a particular row or a particular column, we don't necessarily have to visit the same cell, so we don't care about saving the previous state, so we can just overwrite it. So we'll use the existing array for that. I less than n, increment I, and then for j is equal to 0, j less than m, increment j. Right. So if let's just change. Do we want to do that? Sure. Just to make it simple, just rename that to m. So if m of I of j, if it is equal to 1 and I is greater than 0 and j is greater than 0, then what you're going to do is we are going to m of I of j will be given a new value based on this right here. So it would be math dot min of m of I of j. So let's just look at the previous value on the diagonal, and let's do the same here. Right, and once you get the minimum of all of this, you would just want to add 1 to that. Right, perfect. And once this is done, you would want to add that to the result. So result plus equals the particular value that you're looking at. So the current square that you're looking at represents, oh, these are the number of the size of the side with which you can actually form a particular square, but after every single iteration you need to add that to the result. So that's the reason why you need to add this step right here. Okay, so I think this looks okay. Let's compile this and see if it's okay. The first test case is okay. Everything else is okay as well. Awesome. So let's talk about the space and time complexity. The time complexity of the entire solution is n into m, since we are going through all of the cells in the matrix that's provided to us. And the space complexity of the entire solution is of 1, since we're not really using any additional data structures to store information. Awesome. If you have any questions, please let me know in the comments below. Don't forget to subscribe. I would really appreciate that. I'll see you all in the next video. Peace.